Good afternoon. First, I would like to thank the organizers for this excellent meeting, very meticulously planned. And I would like to thank the community of exoplanet atmospheres and exoplanets in general for this extremely rapid progress we have made just in the past decade. And you'll see what I really mean by that. So here are my co-authors. They've put in a lot of work in various aspects of the chapter and this talk, so I would like to thank them as well. So for me, it's incredible that we are at this stage. We are already talking about processes within atmospheres of exoplanets. Okay, we are talking about non-equilibrium processes. We are talking about their molecular abundances, their elemental abundances, and almost at this stage where we are beginning to make connections with planet formation. And all this happened within just about the last 5 years. Okay, this is incredible. So let me start with a little bit of a big picture. So we know from Deborah's talk and from the various sources in literature that exoplanets are extremely diverse in their macroscopic properties, okay, in their masses, sizes, temperatures, orbital characteristics, and so forth. We know that. And here's just a collection of images demonstrating that. And we also know of several oddballs in exoplanetary systems that have no analogs in the solar system. Okay, so this, this is a representation of the extreme diversity that's out there. Now, the question at the new frontier, as I see it, is to go one step further, okay, going from macroscopic physical characteristics to asking the fundamental questions about their atmospheres and interiors. How chemically diverse are they? Okay, and can we say anything about the fundamental processes operating within these planets? And can we say something about how the atmospheres and interiors can be related to their formation environments and processes? Okay, just as a way of big picture, this is an outline of everything we have done in exoplanet atmospheres over the past half a decade. Okay, so we start with spectral observations. We can use modeling and atmospheric retrieval techniques. We can derive chemical abundances and temperature profiles of these atmospheres. And then from there are lots of different atmospheric processes that we can begin to constrain, and all of them are listed here. Okay, we can do chemistry, we can study thermal inversions, atmospheric dynamics, clouds, hazes, and so forth. Now, if we have the good fortune of additional information about their masses and radii, as we have for transiting planets, then we can compare against internal structure models, and we can go all the way down this chain here. Okay, we can start to understand things like mineralogy, plate tectonics, habitability. This is way in the future, but I just want you to know what's the path we are moving on. Now, an additional piece of information is the star comes from the star itself. If we have the stellar abundances, we can relate the atmospheric abundances to the stellar abundances and start to put some constraints on the formation conditions and migration conditions of these planets. So this, according to me, is the big picture of the field. We have not explored the entire map yet, but we have done a good deal of work in this atmospheric characterization part of the whole scene. Now, in today's talk, I'm not going to talk about all these things. Okay? I'm going to pick and choose. I'll focus only on atmospheres and only on some of these topics here. So if we want to do atmospheres of exoplanets, what are the targets we have out there? So here's, I'm showing a continuously evolving picture of the planet mass and orbital separation diagram. So you can see the planets from various detection techniques color-coded. So you have transiting planets in the red, directly imaged planets in the blue, and in gray are the radial velocity planets. The mass in that case is just the M sin I. So the key point is that we can study atmospheres as of now of only planets that are either transiting or are directly imaged that we can take spectra of. And this is the geometry. Deborah already mentioned about this in her previous talk. If the planet is transiting, in both these situations, you can get spectra of the atmospheres of the planets, so we can study their elemental abundances and so forth. Of course, if the planet can be directly imaged, then you just take a spectrum directly from the planet. Now, I'll touch upon in my talk just the beginnings of what we think can be characterization of radial velocity planets as well. We are just beginning that field, so I'll touch upon that as well. Now, a brief slide on this spectral space. So here I'm showing you an electromagnetic spectrum. It's a nice plot made by my co-author, Heather Knudsen. So in different parts of the spectrum, electromagnetic spectrum, you get different constraints on various different properties of these planets. Okay? If you're in the UV, one can study atmospheric escape, Lyman alpha absorptions, and things like that. If one is in the visible, there are several absorbers we can constrain that have strong spectral features in the visible. Now, most of the constraints to date on exoplanet atmospheres have come from infrared studies. Okay? And I've listed a few of them, a few of the cases here, but I'll go into more detail in later slides. So just to give you a sense of scale, today we have about 50 planets whose atmospheres have been observed in the infrared. We have 50, that's a very big number. Considering that the first direct light from a planet was discovered only in 2005. It was about 8 years ago. Okay? And we already have 50 planets. Not all of them have great constraints, but still at least one data point. So here's an outline for the rest of my talk. I'm going to start with theory, some basics on what we expect to observe in these things, and then I'll dive right into the various inferences we can derive for each of these classes of planets. OK, here's a theory, atmospheric theory 101 for you. This is an equilibrium calculation, a model to calculate a spectrum of a planet. Okay? So here are a set of equations: hydrostatic equilibrium, radiative transfer, radiative convective equilibrium, and then equation of state. So it's very easy. You solve these sets of equations. But then the opacities comes from a combination of the chemistry and the line absorption. Okay? So here's a part showing how you calculate the chemistry. You basically minimize the Gibbs free energy of the entire system, given your elemental abundances and your molecular abundances. Sorry, elemental and molecular species, you can minimize the Gibbs free energy of the system and calculate their abundances. Now, you put these things together and put some boundary conditions in. Here are several model parameters, and then you solve it. Okay? So this is how you calculate a spectrum of an exoplanet. The theory in this regard came much before even the first exoplanet was discovered. Okay? From the late 90s, theory has been around. And we have several sophisticated models currently that are in use. Now, you can take this one step further and say, if I relax the constraints of equilibrium, be it radiative equilibrium or chemical equilibrium, can I still calculate atmospheric spectra? The answer is yes. Several parameterizations of pressure temperature profiles and molecular compositions have been proposed in the literature, and they basically amount to saying P is a function of T, that's the pressure temperature profile, and then you reduce several model parameters that were otherwise present in equilibrium models. All those parameters now go into the analytic pressure temperature profile. Similarly, you can parameterize the chemical compositions as well, and you reduce some computation time issues and so forth, but you are still left with some free parameters. So there have been several models in the literature taking this approach as well. The reason this approach is used is where you want to retrieve the free parameters, pressure temperature profiles, and molecular compositions from the data, as opposed to assuming equilibrium. Okay? I'll get to that in a later slide. So that's a very brief tour of theoretical models. Now, of course, you want to know more about atmospheric theory. Here you go. Okay? So a lot of theory has been done on all these aspects: equilibrium and non-equilibrium chemistry, temperature structures, clouds, hazes, dust, atmospheric dynamics, 3D models, exospheres, so forth. Okay? I'm not going to go into the details of all this in this talk, but should you need any information, all the references are there, at least the most important ones. I would like to point out the most important exercise in all these are finding high temperature opacity line lists, be it from ab initio calculations or from experiments. Okay, that's the centerpiece of all we are trying to do. And then there are several groups that are actively working towards getting us good line lists. And then we can do all the theory we want. Okay, so in the rest of my talk, I'm not going to deal with all these aspects that I've listed here. I'm only going to touch upon two very basic aspects, which is temperature profile, chemistry. Okay, the first 2 points there. Okay, temperature structure 101 for highly irradiated atmospheres. So these are some temperature profiles calculated from equilibrium models. So you can see pressure is going down as you're going up in the atmosphere, and this is the temperature. These are for some standard hot Jupiter atmospheres. Now you'll notice that there are some profiles go monotonically decreasing. Some have these kinks. Now what's going on? Now there is some very simple back of the envelope calculations you can do to justify to explain each of the different components. You can divide this atmosphere into 3 layers. The bottommost layer is just the diffusion approximation, which means at very high optical depth, the stellar flux is not reaching there. So you basically have no flux. The F is 0. So in the diffusion approximation, you just get an isotherm for the temperature. Similarly, at very higher up in the atmosphere, it's a low optical depth regime, so you just get the skin temperature, again, asymptoting to an isotherm. That's this. And this is where all the action is, in the central region. And that's where all our infrared observations are probing. So we can use, in principle, infrared observations to constrain these temperature profiles, whether they're going up with altitude or whether they're going down. And this is where the concept of thermal inversions comes in. If there is an absorber in this part of the temperature space, pressure space, which can absorb in the visible, then it gives this local increase in temperature, and that's a thermal inversion. And we'll talk about this in detail. So people have tried simulating these profiles analytically. There are several references here, and you can have analytic gray atmosphere approximations. Now, here's the summary of this entire tutorial on temperature structures. Measuring temperature structures allow us to constrain the thermal, chemical, and radiative processes happening in that part of the atmosphere which is accessible to infrared observations. Okay? So you should remember that. Now, the second piece of theory I want to talk about is chemistry. What do we expect for atmospheric chemistry in hydrogen-rich atmospheres? This is just showing a contour diagram over the pressure and temperature space of hot Jupiters and hot Neptunes. So you can see the red is mixing ratios of 100 parts per million, 10 to the minus 4, and each other color is going one step lower in 1 decade lower in mixing ratio. The summary here is that at every temperature you can think of for hot Jupiters, you expect to have a lot of water. Okay, that comes from the assumption of solar abundances. And then at high temperatures, you're supposed to have a lot of carbon monoxide. At low temperatures, you're supposed to have a lot of methane. Okay, and this column here is showing what happens if you increase the abundances by a factor of 30 relative to solar. So here's the punchline for this part of the theory. For solar composition atmospheres, which is what we have been assuming all along, water should be dominant at all temperatures. Carbon monoxide should be dominant at high temperatures. Methane should be dominant at low temperatures. That's it. So we go from there. Okay, very basic theory. And now, armed with this sort of basic principles of theory, we just go forward and try to estimate the pressure temperature profiles and compositions for these planets and see if we find anything close to what we expect. Okay, so now let's move into the major results over the past half a decade. So I'm going to go down this list here from now on. So here's an outline for the advances in hot Jupiter atmospheres. Okay, we have been able to constrain temperature structures and thermal inversions in this atmosphere. So we have been able to constrain molecular and elemental abundance ratios. We have been able to observe phase curves and constrain atmospheric dynamics, so on and so forth. Again, I'm not going to talk about all these aspects in this talk. I'll pick and choose. Let's start with what we know of temperature structures. So we just went through this slide. So we know that temperature structures can go either way depending on what absorbers there are in that part of the atmosphere. Now, here's the basic principle of the TIO-VO hypothesis, if you have heard about this in the literature. TIO and VO are molecules which are strong absorbers of visible light. So if they are higher in very high temperatures, they can be present as in gaseous form high up in the atmosphere. So they can intercept incoming stellar radiation and cause a local increase in the temperature. So you can get thermal inversions. Here's a cartoon. So this is a profile with a thermal inversion. This is a profile with no thermal inversion. Now the question is, how do you see the influence of these temperature structures in spectra? This is an example. So here I'm showing several molecules in a hot Jupiter atmosphere, and the blue shows the spectrum for a non-inverted temperature profile, and the red shows all the absorption features in emission. So you can see that the two temperature profiles give radically different spectra for the same chemical composition. And the differences are big enough that with the current precisions with our instruments, we can detect them. We can detect the differences. So the first inference of a thermal inversion came from this paper by Knudsen et al. So you can see here the red model is one with thermal inversion, and it is closer to the data than the black model. Motivated partly by this inference, Fortney et al. Proposed this 1D classification scheme, two classes of hot Jupiters, one very hot, very highly irradiated, which you can expect to have thermal inversions due to TiO-VO, and another class called the lower class here, which won't have thermal inversions. So this is a neat classification scheme. It gives observers a very neat way to classify hot Jupiters just based on a few observational inferences. Just using Spitzer IRAC photometry, these are Spitzer IRAC photometry, by the way, one can in principle constrain thermal inversions and classify hot Jupiters. Of course, there are some kinks in the theory. Spiegel et al. Suggested that you could have TiO-VO, but the TiO and VO molecules are heavy enough that they're also subjected to gravitational settling and condensation. Okay, so you could have this band be wider, where there is uncertainty on whether there will be thermal inversions or not. So here I'm plotting the same plot as what Fortney et al. Proposed, but except with planets which have at least 3 or 4 channels of Spitzer photometry. Okay, and what we immediately saw, like a few years after the classification scheme was proposed, that there were a few planets that were outliers to this proposed scheme. All these planets which were supposed to have thermal inversions did not, and this planet which was not supposed to have a thermal inversion was inferred to have a thermal inversion. And there are all these papers. How do you reconcile this? Now, Heather Knudsen et al. In 2010 proposed this alternative, this addition to the classification scheme, where they said that maybe the inversions are influenced by the activity of the host star. If the star is highly active, it could dissociate the inversion-causing compounds in the atmosphere and hence not have a thermal, and hence the planet may not have a thermal inversion. So here they proposed a correlation between the activity and the stellar effective temperature, which is proxy for the irradiation. And they found that based on some nominal schemes for how to claim a thermal inversion, they found that the theory sort of works. The proposed hypothesis of activity sort of works. Now came another proposal from myself and my team, where we found that if you change the C2O ratio of the atmosphere, even if the atmosphere is extremely highly irradiated, TiO won't be as abundant as you thought you would. It would from solar abundance assumptions. Okay. So obviously then the C2O becomes a new dimension for characterization. So in recent work I proposed that in addition to this one-dimensional theory that Fortney et al. Originally proposed, we should have another dimension for the chemistry, for the C2O ratio. And here you can have various different chemical compounds, and I won't go into the detail of the theory, but in principle, you can explain all those contradictions I had talked about before. Now, why the C2O ratio is important, we'll get to in a few slides. So that more or less ends the state-of-the-art of our theory of temperature structures in exoplanet atmospheres, in hot Jupiter atmospheres, to be very specific. Now let's move into chemistry. Now, molecular inferences in hot Jupiters started around 2006. That was after the last PP5. And initially, the inferences were made based on 1 or 2 or 3 points of photometry. So here you can see Bodman et al. Suggested the presence of water based on this one point here obtained with HST, and Tinedi et al. Suggested the presence of water based on 3 channels of Spitzer photometry. But then these data are extremely hard to obtain. The instruments have lots of systematics that one has to be very confident of. So there are lots of debates that are underway on each of these data sets, and I won't go into those details at this point. Similarly, Swain et al. In 2008 claimed detections of water and methane in the atmosphere of another hot Jupiter, HD 189733, that is also mired in debates over the past several years. Okay. One of the more trusted data sets at that time was this Spitzer IRS spectrum, and this is even to date the highest resolution spectrum we have in the mid-infrared for an exoplanet. Okay? And they use that spectrum to claim the detection of water in this atmosphere. Now, you might notice something very peculiar that's happening here. In all these cases, the inferences are made based on fitting 1, 2, or 3 models to a limited set of data. Now, in one of the previous slides, I told you that there are several free parameters in these models, 10 parameters to be precise. Okay? Now, you have very few data points. You have so many free parameters. How are you sure that each of these models is a unique fit to the data? Once we have these data sets by late 2008, that problem became more and more apparent to the people in the field. So the first solution to that problem came about in 2009. This was Sarah Seeger and I worked on this problem, and we came about a parametric model. I showed you parametric models, and this was the first time we introduced such models in an effort to span the parameter space and try to find what is the inherent degeneracy between the parameters, and can we give a population of models and do some statistics on the fits given a set of data. And here I'm showing you just one example of that. Here in black are shown 6 channels of Spitzer photometry. And then you just use parametric models and explore the parameter space of water, carbon monoxide, methane, CO2, and so forth, all the molecules you think would be abundant in a solar composition atmosphere. And the parametric temperature profile can also be explored. So you can see these colors represent different values of this reduced chi-square between 0 and 1, 1 to 2, 2 to 3, and so forth. And you can, in principle, come with populations of models that fit a given data set at a given level of confidence. We are still nowhere near to having a unique fit. There are always more parameters than the data. But at least we know the range of models that can fit a given data set at a required chi-square. So we use this to place some statistical constraints on molecular compositions. We did place some constraints, but at this point, the more important point to take away is that we have the tools to constrain the abundances, not that we can constrain the abundances to any great degree currently. But when we get good data, we in principle have the tools to interpret such data. Now here's a much better spectrum, and this is fast forward 2013. Okay, these are spectra reported this year, and you can see the resolution on this. These are spectra obtained with HST, the wide field camera. Okay, now you can say something more sensible. Here maybe we are actually seeing water here. Same in this planet here in WASP-19. Okay, so the field has moved along like quite a lot in trying to make these observational inferences of molecules, and I just list a lot of papers here which go all the way from photometry to spectroscopy and trying to infer molecules. We still have only limits on molecules and a few detections like this, but nevertheless the field has moved forward. So at this point I would like to pause and draw your attention to 2 major opportunities that we have currently in observations of exoplanet spectra. One is WIFC3, which is what you're seeing in front of you. Okay? The second most important advancement we have made is to observe these atmospheres from ground. Okay? This was considered impossible even just 4 or 5 years ago. And here I'm showing you just a smattering of spectra and photometry. These are all ground-based points, as you can see. Z-band, JHK, Same here. These are all for one planet, WASP-19. And Bean et al. Perfected this technique of spectroscopy, multi-object spectroscopy for exoplanet atmospheres in general. And you can see this low resolution, but still spectrum that we are able to obtain today. Okay, and then there are several other examples like this in the field, especially for photometry. It's common today to get photometry of these planets. Still very challenging, but still very common. Now, I want to tell you what the power of these data sets is. Okay? Here I'm showing you a model spectrum. Take it for any hard Jupiter. And I'm showing you just the photometry available today, all the bands. Several broadband photometric bands, one narrowband, several Spitzer bands. These are not all available, but we have, the instrument is not available, but we have data from cold Spitzer era for several of these planets, and we have HST WIFC3 operational today. The power of this, of having these bands is that you notice that all in these bands, the ground-based bands, the spectrum is peaking wherever you see. That's a very curious fact, actually. The reason you see those peaks is because there is no molecular absorption or little molecular absorption in those bands, so you can see all the way down to the bottom of the planetary atmosphere where the temperature structure is an isotherm. So the power of these band passes is that you can constrain extremely well the lower atmospheric temperature profile of these atmospheres with those bands, and then the rest of the molecular band passes could be used to constrain the molecular composition. Earlier, it was a degeneracy that we had to deal with, but now the degeneracy is partly split. Okay? So this, in my view, is a major advancement we have had in the field, and I'll show you an example of that. In 2011, we had the good fortune of having all data in all those bands available for this planet WASP-12b, and remarkably enough, we could use all those bands to place these constraints on the molecular abundances for the first time to this level of precision. And you can see water, CO, and there were other molecules as well. But now we can start talking about elemental abundances, the C to H ratio, O to H ratio, the C to O ratios, and so forth. The remarkable conclusion from this entire study was that we could put only an upper limit of water, and that was 100 times lower than what we had expected. Remember the tutorial I gave you about chemistry? You expect water to be there at all temperatures, but we found water to be 100 times less, and we found methane to be 100 times more. That was remarkable to see in this atmosphere. The constraint that led to is to have a C2O ratio greater than or equal to 1. And that's remarkably different from a solar abundance atmosphere, which has a C2O ratio of 0.5. So that's where you, whenever you hear these carbon-rich atmospheres, carbon-rich planets these days, this is where they're coming from. Now, this result has been debated a lot recently as well, because again, as I said, these data are extremely hard to obtain. The systematics are extremely hard to get over. So several people have challenged some of the data points. There is still work in progress. But the key point is not whether we have discovered a carbon-rich atmosphere. The key point is that we have been able to make a measurement of the C2O ratio in an exoplanetary atmosphere. I'll tell you why that is important. Two reasons. The first reason is why the C2O ratio is important for atmospheric chemistry. Here's a plot showing the mixing ratios as a function of the C2O ratio for a certain hot Jupiter atmosphere. Okay, for a typical temperature of 2000 Kelvin and a pressure of 1 bar where the observations are probing, you see that as you increase the C2O ratio to close to 1, so this dotted line shows 0.5, as you go close to 1, the water abundance plummets by 2 orders of magnitude. That is not your assumption about a solar composition atmosphere. So we are talking about atmospheres that can be radically different from what we had imagined when we started out in the field. Okay, and then there are several hydrocarbons that pop in as you go to higher C2O ratios. This is important to know, regardless of the result of WASP-12b. Okay, you want to have this picture in mind when you go out and measure molecular abundances in these atmospheres. So that was a reason number one. Now, the second and more important reason why it's important to get C2O ratios is the following. So this is our good old friend, Jupiter. And you see the abundances measured with the Galileo probe in the late part of the last century. You can see abundances of all the elements, these noble gases, carbon, nitrogen, sulfur, but we don't know the abundance of oxygen in Jupiter. It's remarkable that we don't know the abundance of oxygen in Jupiter while we are trying to measure C2O ratios in planets around other stars. Okay, this is just a remarkable fact. And there are several theories proposed to explain the C2O ratio, potential C2O ratio greater than 1 in Jupiter. We don't know this yet. The Galileo probe is going to measure that for sure. But the point is, if C2O ratio in Jupiter is in fact true, we don't have a complete model of the solar system to explain it today. Now you may ask, why is it the case that we can't do this for Jupiter, but we can for an exoplanet? Here's the answer. It's actually very trivial in hindsight. These are all solar system planets shown here on the top left corner. And then we have several hot Jupiters here. All the hot Jupiters are thousands of Kelvin hotter than the condensation curve of water. But Jupiter is much cooler. All these giant planets are much cooler than that. So we can't measure. All the water is buried deep in Jupiter's atmosphere, whereas in exoplanet atmospheres, they're all in gaseous phase, accessible to spectra from Earth. So here's the takeaway message that I want all of you to know, that we can measure these abundances better. This is only one of the very few quantities that we can measure better in an exoplanet than we can in our own solar system. I think this is amazing. And we have, based on just the limited data we have gone ahead and tried to put some nominal constraints. These are by no means rigorous constraints, but we do what we can. So I tried to do this last year for 6 planets, and here are some limits. Don't take this too seriously. This is still work in progress. We still need more data. But you get the spirit that we want to do this. We want more data. If you're an observer, this is the motivation for you on why we want to get this data. Now, OK, we can find C2O ratios that we can't do on Jupiter, but what's the big deal? The big deal is that we can now start placing constraints on planet formation. We have seen in the talks of Ted Bergen on the other day, if you have a protoplanetary disk, the chemistry in the disk is changing with separation from the center. Okay? Now, depending on where the planet formed, you can have a very different chemistry. And the C2O ratios is one of the trademarks, one of the tracers of that chemistry. So if you can measure it in an exoplanetary atmosphere, a giant planet atmosphere, you can, in principle, start to make some connections to its origins. OK, so now let's move on to atmospheric circulation on hot Jupiters. That's the next topic. And on all the rest of the topics, I'll go very fast, couple of slides per topic. Okay, let's start with atmospheric circulation. Hot Jupiters are expected to be tidally locked, so there should be high gradients, thermal and chemical gradients between the day sides and night sides. Also, the planet's slow rotation means that any dynamical patterns should be global in scale. So there are several 3D general circulation models that have been worked upon in the literature over the past decade. Now, I'm not going to go into any of the detailed theory. I'll just show some basic results to begin with. Okay? So we can today observe phase curves of transiting planets. Okay? This is an iconic phase curve from 2007, Knudsen et al. 2007. And you can see this brightness map based on some nifty inversion schemes from Cohen and Egal. Okay? So now we can map out weather on exoplanets, hot Jupiter atmospheres. I think this is incredible, too. And then here are some theoretical results. Showman et al. Showed this is actually a prediction that in hot Jupiters, you will see the hot spot not at the substellar point, which is the point facing the star, but it will be shifted downward in the wind. Okay, this shift is about 50 degrees from the substellar point. That's a prediction from general circulation models, and you see that in the phase curves. Here a match to the data. You see the peak closely aligned with what you see. I think this is a remarkable thing, too, that GCM models can predict things that phase curves can observe to that level of detail. Now, the second point I want to highlight in atmospheric circulation models is a very basic concept that if the radiative time scale is shorter than the advective time scale in circulation, then you will have all the energy radiated on the day side. So you should see very high day-night temperature contrasts in hot Jupiters, whereas if the advective timescales are shorter, you'll see very low day-night contrast. And that's a prediction from theory, and that sort of works with observations as well. Here is a plot from Cohen and Egol. You see that highly radiated planets, this temperature is a proxy for the radiation, have higher day-side temperatures, which means lower circulation, less efficient circulation from the day side to the night side. So these are all consistent, mostly, with the phase curves that we're observing to date. Okay, so these are the only two basic results from the atmospheric dynamics side that I want to focus, that I wanted to tell you today. And now I want to move on for just one slide to mention that along with molecular inferences, we have also made a lot of atomic inferences in these hot Jupiters. There have been predictions that sodium and potassium should be abundant in these extremely radiated atmospheres. We have seen it. We have seen in some systems from ground, and we have seen potassium from ground as well. Very recently, I have a listing of all the papers here over the last decade, starting with the first detection from Charbonneau et al. 2002. I want to spend another slide talking about clouds and hazes in these atmospheres. Now, this is another iconic result from Pont et al. And continuing on by the same team, latest being Singh et al., where you see that a continuous Rayleigh scattering slope very consistent with this data set. In this atmosphere of HD 189733, no spectral features in sight whatsoever. And they use this to infer the inference is one of a Rayleigh scattering atmosphere with a hazy atmosphere. Now, another very recent result as of this year, as of a few weeks ago actually, is this first measurement of a differential geometric albedo, albedo being very high in the blue, but not so much in the red. Okay, this gives the impression of a hot Jupiter appearing blue. Now, imagine that. So that's this result just from this year, also using HST. Now, there were several other geometric albedo measurements using Kepler data. You know, the Kepler bandpass is centered in the optical. There have been a few inferences like that, so I list them here. Now, in just the last slide on hot Jupiters, I want to introduce to this remarkable technique which has a great potential to the future, and I promised you that I'll show this, which works for radial velocity, non-transiting planets as well, and that's the cross-correlation technique. Now, you know this planet is moving very fast around its host star, so even if it's not transiting, you can see the signatures of its atmospheres blue shifted as the planet is coming towards you. Now, if you can do some very clever cross-correlation with a template spectrum of an expected molecule, you should, in principle, be able to detect that shift. And that's exactly what this team has done. So you can see the RV shifted. This is just showing a contour of the statistical significance of the cross-correlation. You can see these dark regions showing an RV shifted CO bandpass. And this is for a transiting planet. So we know it's transiting. We know its orbit very precisely. And they've detected CO at very high significance, and have also used it to infer strong winds on this in this planetary atmosphere. But the more remarkable thing is that they could use the same technique on a non-transiting planet. That's this, Tau Boötis b. And they could also detect CO. Okay, so the technique works, and in the future, this could be a very powerful technique for characterizing many planets. So to give you a sense, there has been no detection of molecular, CO at 6 sigma from other methods, even with Spitzer. Okay, and this is the only technique that could do it to date. So the future is only very bright. There will be a couple of slides on directly imaged planets. We don't have as many inferences for directly imaged planets as we have for transiting planets. In the discovery space, direct imaging is doing pretty well, but for inferences, here are a couple of them. So there are the discovery papers have a lot of photometric points, and then there is a lot of spectroscopy also happening, high-resolution spectroscopy for directly imaged planets. And here I just list all the inferences for HR 8799 system, which is the only system for which detailed studies have been conducted. There have been claims of non-equilibrium chemistry. They see much lower methane they expect to see than they expect to see. We see thick clouds in these atmospheres, high-resolution spectroscopy. Deborah showed this plot by Konopacki et al. Very remarkable work where they could detect atmospheric chemical features with high-resolution spectroscopy. And then recently, there have also been results of atmospheric retrieval on this system. In the next couple of slides, I want to wrap up with just talking about small planets, Neptunes and super-Earths. Now, the motivation is the following. We know from Kepler and ground-based surveys that Neptunes and sub-Neptunes dominate the field of exoplanets, at least the ones discovered so far. So understanding what their interiors and atmospheres are is a prime question. Now, the key question, though, is that we know gas giants are hydrogen-rich. We know, just from interior models, we know ice giants could have atmospheres that are hydrogen-rich. But we don't know what the atmospheres of super-Earths are. Are they like terrestrial planets, very dense atmospheres, or are they hydrogen-rich? So these are some of the questions we want to address going forward. So I just want to take you through a couple of slides on key results. To give you a sense, we have about 10 hot Neptunes, about 10 super-Earths that we know of to date, transiting ones which have mass and radii. And we have atmospheric characterization for exactly one hot Neptune and one super-Earth to date, decent atmospheric characterization. So I just want to talk about those two cases here. So I showed you this plot, chemistry in hydrogen-rich atmospheres. At low temperatures, you expect a lot of methane and very less CO. That's what this plot shows. And if I plot temperature profiles on this, this is the temperature profile of a hot Neptune called GJ436b. So you expect to see a lot of methane and not much CO in it. But then what do we see? So this is just the hot Neptune and its parameters, but the gray curve here is showing a solar composition spectrum where there is a lot of methane absorption, but the data is more than 10 sigma away from the spectrum. So solar composition and equilibrium compositions don't fit the data, okay, way off. The only way we could fit the data is if we had extreme non-equilibrium chemistry or some process which is getting rid of the methane. So the green curve here does fit the data, but it has 1,000 times less methane than we expected. And it has about more than 1,000 times more CO than we expected. The only way it can work is there is some severe non-equilibrium chemistry happening, some non-equilibrium processes. So here I show this KZZ, the vertical diffusion coefficient, as and then the CO mixing ratio. And what we showed in this study, both Stevenson et al. And my work with Sarah Seeger, that in principle you can explain the CO with this non-equilibrium chemistry, but we still cannot explain the methane. Now, there are several works that have challenged the, actually there's one work that has challenged the observations itself, but it's still a work in progress, lots of debates going on. There is a recent, just as of last month actually, hypothesis from Julie Moses et al. Moses et al., who say that maybe very high metallicity, 1,000 times solar, very radically high metallicities could explain the data. Okay, that's still another interesting idea, and there are several theory, there's a lot of theory work that's also happening to reconcile this planet and hot Neptunes in general. But that's the state of the art of observational inferences for hot Neptunes. Now the last slide, last two slides is about super-Earths. Now here's a canonical, the canonical super-Earth that we have to date, the only one for which we have atmospheric inferences to date. Here I'm showing you some mass radius diagrams plotting all the super-Earths that we know of to date, and here's GJ1214b. It sits above the water curve, so one would expect it to have a hydrogen-rich atmosphere. Now we go ahead and try to see what its atmosphere would look like with spectroscopy. You can see the difference here. If it has a hydrogen-rich atmosphere, the scale height will be large, so you should see an extended atmosphere. If it's a water-rich atmosphere, then you should see a very small scale height. The problem, so Bean et al. In this revolutionary work used a multi-object spectroscopy to obtain a transmission spectrum for this planet, and here's the data set. You can fit a flat horizontal line through all the data. If you're not surprised enough, wait till the next slide. But here you can fit a flat line. You can fit several kinds of models, a water-rich model, it's 100% water model. And you can fit a flat line, which is, let's say, a cloudy model with no atmospheric features. But the good thing is that you can rule out a solar composition model. You can rule out a hydrogen-rich atmosphere without clouds. Okay, so that was the result from this work, and then there are several observations. I think this is the most observed planet to date. the GJ1214b, and here's what I mean by that. You see the data in different symbols and so forth explained here. All the data all the way from 0.7 to 5 micron can be fit with a straight line still. So we are still where we started. It can either be a heavy mean molecular weight atmosphere or one with clouds. The positive part is that there are theoretical studies which say that you can, in principle, tell the difference between the two with more HST data. And I'll leave you with this conclusion here, that HST WIPC3 observations would require 10 orbit, 10 eclipse, 10 transits of this planet, and they can give you enough precisions to tell between the two scenarios. OK, I'll end with this slide here. The future of exoplanet science is clearly going in two directions. One is detection of smaller and smaller planets orbiting nearby stars, and hopefully smaller stars. So then we can go ahead and characterize their interiors, atmospheres, and so forth. And then characterization of atmospheres of exoplanets for all the reasons I talked about in my talk. And we want to understand their processes, but also linked to formation and so forth. Now, here are several efforts that are underway in the future, in the next decade. All these efforts will find us tons of planets around nearby stars. At least that's the hope, and that's the design. Tests, there is CHEOPS, there are ground-based efforts like NGTS and so forth, led from here in Europe. And on the atmospheric characterization side, there is James Webb. This also makes a very important case that ECHO gets selected because James Webb cannot follow up all the planets that we would know at the time, even the planets that we know today. So we need a dedicated mission to do atmospheric characterization, and ECHO is supposed to do that. And the big telescopes that are coming up from ground will also have enormous potential to help us in this effort. And I'll leave you there. Thanks.
Thank you for this nice review. It's pretty amazing that we can start to detect molecules in atmospheres. So, questions? Aiken.
Heike from DLR. It has been really a great talk. Thanks a lot. I just want to know one question. In your previous slide, you had the formula for the scale height. And you assume you know the gravity of your planet.
Yeah,
and
yeah.
I was wondering where you get this from.
A transiting planet, they're confirmed transiting planets where you know their masses and radii.
Yes, I agree. That's why I think in your list of future missions, you should include those that give you the G, because the uncertainty in the gravity for most planets so far is much larger than your choice of molecular weights.
Good point. Thank you.
The left.
Hi. Chi Wang from Yale University. You mentioned you can measure the bulk density from radial velocity and the transiting. You can also get the chemical composition from the transiting spectroscopy. How are you use this information to probe the internal structure of a planet? I remember you mentioned it at the first couple of slides. Can you elaborate on that? Do we currently have a technique of doing that? If so, can we apply it?
So the internal structure constraints today mostly come from mass and radius only. Right, that's the bulk structure you get. But if you know your planet, so if you see this slide on this slide right here, you know just from the mass and radius that this planet needs an atmosphere, right? And the only lighter element than water we currently have in our models is hydrogen. On the other hand, from the spectroscopy, we rule out an atmosphere of hydrogen without clouds. So tomorrow if we find a water-rich atmosphere, we still have this problem on trying to reconcile with that mass and radius. So there are some interesting paths in that direction that one can think of. So atmosphere gives you an additional constraint in addition to mass and radius in trying to constrain the internal composition of the planet.
From the top.
Quick comment, Neil Deacon, MPIA. You didn't mention isolated young LNT dwarfs, which have often similar masses, gravities, and effective temperatures as directly imaged exoplanets, but can get much more easily get data without AO or any more complicated techniques to study their atmospheres. And there's a couple of nice posters here by Farty, Bundesley, and Cruz on that subject?
Yeah, that's actually a very interesting topic, and I had several times contemplated getting into that area. T dwarfs have very good spectra. We could use all our retrieval techniques, yes, to infer their atmospheric compositions. I bet someone in this hall is working on that topic right now. They may not be saying it out, but yeah, I expect to see those papers coming out anytime. I myself tried to do that. But yeah, we have the tools to address that problem.
One question.
May I add a comment? Okay, nice talk. So on the upper atmosphere atomic species detection, there are some detection of silicon, oxygen species. I think you want to add that. So my question is, it's great that you can detect the CO in the Jupiter's atmosphere. I wonder what kind of observation will take to determine CO abundance in the atmosphere of, say, habitable planets.
Habitable planet?
Yes. And abundance, not just the detection. Determines the mixing ratio, for example.
I assume you realize we are quite a ways away from detecting even atmospheres of...
So what kind of observation, future telescopes that can do that?
So JWST will get close to M dwarfs. Okay, planets that are like super Earths around M dwarfs. JWST should be able to do it at some level. But if you want really terrestrial-sized planets, we could push JWST in the same way that we had pushed Spitzer and Hubble beyond our expectations. Maybe that'll work. But I bet you need some kind of a TPF to do it at the end of the day.
Okay. On the left. Then.
Hi, Andrei Jean from MIT. So as far as I know, all of the retrieval methods assume that the pressure, temperature, and mixing ratio profiles are kind of constant along the limb of the planet.
And vertically as well.
Yeah, vertically as well. So what do you think is the impact of this assumption on the transmission spectra? And as in the future the data quality gets better, at what point do we have to relax this assumption?
That's a very good question, actually. So we have been worrying about this ever since the first time we did it. So there are two things. One is the data. So your models have to be justified by the data. We have a few photometric points. There is no hope, even if you assume everything to be uniform, there is very little hope to get good constraints. So it's purely data limited at this point. Our models have the tools to include parameters for this vertical profiling if you had more data, but we don't have that data. That's one thing.
What about GWST?
Probably with JWST, yes. The second point is that for the hot Jupiters that we are dealing with right now, it's a very safe assumption. Because I showed you this chemistry plot and the temperature profiles on those. They lie in a region where any sort of inhomogeneities are homogenized very quickly. Like the temperatures are so high that you get a very robust chemistry no matter how you cut it. Right? But it's going to be a problem for low temperature atmospheres for these exo-Neptunes, like GJ436 and cooler. That's going to be a problem, and we'll be working on it.
3 last quick questions, 1, 2, and 3. So
can you hear us? Can you hear me? Okay. So you showed some modeled spectra and observations in the mid-infrared range. And do you think you can possibly tell us the importance of doing mid-infrared? Not just near-infrared up to 5 micron. This is actually an important issue for SPICA, the proposed next infrared space mission led by Japan and Europe.
Right. The infrared region you're talking about beyond 5 microns, we actually have gone till 30 microns, like with the old Spitzer, with cold Spitzer. There was one point, the MIPS point was at 24 micron. So those points do give us extremely good constraints on the molecular chemistry. So yes, something like SPICA would be very good for the field.
Thank you.
Here in the center.
Hi, Sam Quinn, Georgia State University. You mentioned that measuring the C to O ratios potentially gives you a sort of leverage over planet formation theory. But of course, there's still some remaining uncertainties in formation and migration theories. So my question is sort of 2 parts. One, do the currently measured values of C to O in hot Jupiters give you any sort of indication about whether they acquired all of their material far out in the disk or possibly continued to accrete some material close in as they migrated inward? And regardless of that answer, do you have any suggestions for maybe complementary observations, particularly atmospheric observations that could give us clues to their formation histories?
Yeah, so answer to your first question, it's still too early in the process. We are still barely being able to measure the C2O ratios. But the good thing is the C2O, I think we are in a fortunate situation, is that the C2O of one boundary is a very strong boundary. It's very hard to get a C2O of 1 or higher. Okay, but if you do see planets like that, they have to be formed in only 2 ways, at least based on current literature. They either have to be formed very far out in the disk where the gaseous C2O, effective gaseous C2O of the disk is close to 1. And this was talked about in earlier talks in this conference. And this was proposed by Oberg et al. Or there is some mechanism that we don't understand that is causing turbulent fluctuations in the C2O ratio of the disk, along the disk. So either way, it's something that we haven't expected. And I mean, it's too early in the process, but I bet theorists will be working on it from now on. Second question, yes, in addition to C2O ratio, the future is going down to other elements like the nitrogen abundances. In disks, actually, I started working with some disk community folks as well, where HCN to H2O ratios are routinely measured, right? We might want to do that for hot Jupiters as well. HCN has strong features in the WIFC3 bandpass as well. And there are some papers where we have already tried to do it, but the constraints are not very good yet. But I think that's the future.
Deborah, the last question.
Hi, Manu. So could you remind me, there's this incredible statement that you made that we're learning about the chemistry of exoplanets better than we are about Jupiter. And I just wonder, technically, what is it? Why can't we just turn Spitzer or use the band passes that we have on ground-based instruments to observe Jupiter and get some sort of a disk-integrated spectrum? Why can't we do better?
Yeah, actually, we have tried to do a lot of that in the past several decades. The fundamental problem is the water layer in Jupiter's atmosphere is below the 10-bar level. It's very deep in the atmosphere. So you literally have to send a probe, and the last time we tried, the probe failed before getting deep enough. Okay, so that's the technical problem. And it's the same for all other giant planets. It's actually worse for all other giant planets in the solar system. So the water is not up in the atmosphere. For hot Jupiters, it's all the way up in the atmosphere.
Okay, let's thank the speaker.